Welcome back to the Breakout Lab series. This is Breakout Lab 8, and in this lab, we are going to be looking at Lab 7. We were doing user-defined functions with passing parameters by reference and value, and we're going to continue that, but specifically in this case, we're going to be looking at collision detection. We're going to be, for our breakout game, determining if our ball has hit, for this lab, one of the walls. But we'll use a wall like a rectangle. In general, what we're looking at is a method for determining if a circle has collided with a rectangle. All right, so let's get started. So this is going to be kind of disjointed at first, but hopefully it'll all come together for you at the end. What we're trying to do to start with is pick a spot on the rectangle that's closest to the center of the circle. So what we want to do is identify an XY coordinate, and we have to do that one coordinate at a time. In other words, the X coordinate and then the Y coordinate. So in this case, we're going to use the circle's X, which is the center of the circle. And if it's less than the rectangle's X, which is the bottom left corner here, or the left side, then we know the circle is to the left of the rectangle. And we would say that the test X coordinate that we want to use is going to be the rectangle's X. And when we say test coordinate, we mean the coordinate that we're going to use to test with the center of the circle, right? So this will fix our X to somewhere on the left edge, right? If our circle's to the right, then our circle's X coordinate would be greater than the rectangle's X plus its width. And so we would know that our test X is going to be somewhere on the right edge of the rectangle. Right? If the circle is somewhere between the X and the X plus width of the rectangle, then we'd use the circle's X coordinate as the X coordinate for our test spot, test point. All right, now for the vertical, it's very similar. If the circle's Y from the center of the circle is less than the rectangle's Y, then we know that the point we want is somewhere on the bottom edge of the rectangle. So we would take the rectangle's Y. If the circle's Y is greater than the rectangle's Y plus its height, then we know the point would be somewhere on the top, or the rectangle's Y plus its height. All right, and then if the circle's Y is somewhere in between the rectangle's Y and the rectangle's Y plus its height, then we would use the circle's Y for that coordinate. All right, so putting those two coordinates together, we would end up with a spot somewhere on the rectangle that's closest to the center of the circle using the X and Y coordinates. And you can see the different X and Y coordinates is using these abbreviations for like rectangle X, rectangle Y, rectangle width, height, circle X, circle Y, right? But you can see the different combinations that we would end up with that would give us that point on the rectangle that we could then determine. And what we're going to look for next is going to be distance. All right, so to determine distance, we can use some simple linear algebra. We're going to use Pythagorean's theorem with a right triangle here. The hypotenuse then is the line going from the center of the circle to that test point that we've identified on the rectangle. And so we can use a simple Pythagorean theorem to do that by taking the difference of the X coordinates. So in other words, one of the circle X minus the test X, or vice versa, it doesn't matter. But we take the difference of that and square it, plus the difference of the two Y's and square that, and that would give us the distance along this line. All right? And in the end, what we want to know is that distance less than the radius of the circle? If it is less than, then we know that the circle is overlapping the rectangle and we've had a collision. So if the distance is greater than the radius, then the circle has not made it to that rectangle yet. All right, so once we have the fact that there is a collision, if we determine that the distance between the 2 points is less than the radius, now we want to know, well, what part of the circle has impacted the rectangle, or in this case the ball, and this represents like a block in our breakout game. All right, so we want to know what part of the circle is touching or overlapping, and that will allow us to create a nice rebound. All right, so we can use a little trig here. We can use a tangent with right triangles again to determine what this angle is between the x-axis and the hypotenuse. So we'd be, in this case, measuring this angle right here. All right, so we're going to do that using some C++, obviously. And so C++ gives us an arctangent2 function, which will return us the arc expressed in radians, with radians being equivalent to 1 radian is equivalent to 180 divided by pi degrees. So what we can do is, if we take that arctangent of the difference of x and difference of y, so that's similar to Pythagorean's theorem, but taking a tangent instead of the square root. And so what we get back, this would be called a theta, and if we or the radians. And if we take that and multiply it by our 180 divided by pi, we will get degrees. Now the only problem with these degrees is these degrees are relative to the x-axis, with the x-axis being 0, and we want 0 or 360 to be up here on the north. We want a cardinal direction, or cardinal degrees. And so what we need to do is rotate that number to the left 90 degrees. We do that by actually subtracting the degrees that we get here from 90, and that will rotate it to the left. Now we may end up with a negative number if we cross the 0 boundary, and we can fix that just by modding that result with 360, and that will get rid of our negatives. And we don't need to really understand all the math here, we just need to put together the formulas. And we can see here, this little table just gives us some examples based off of the circle center being at 0, 0, and then the coordinates for the point that would represent on the triangle, on the rectangle. In this case, say 50, 50 would mean we would move over 50 in the x and then go up 50 in the y. So we can see our difference, x and y, are both 50. Our arctangent of that difference is a 0.79 radians. All right, we multiply that by 180 divided by pi, and we get 45 as our angle, so 45-degree angle. Subtracting that from 90, we still get 45 degrees, and modding that with 360, we still get our 45 degrees. And we would see we would have an arrow pointing up at that top right quadrant. Right, so we can go around, and this just tests. So in this case, the point to our rectangle is minus 20 in the x, so we go to the left and then up 50. So it'd be somewhere over here, and we can see how that would work out, right? We get a 1.95 radians, multiplying by 180 divided by pi, we get our 111.8 degree angle. We subtract that from 90, see here we get 21.8. So modding that with 360, and we get a 338.20 degrees from north, right? And that gives us a nice degree 2 there. So obviously these just go around the quadrant. This would be a negative 50, negative 30. We're showing a 239 degrees. Down here we have a 55, so we go to the right and then down 25, and we end up here with like 114 degrees, right? So, and these little arrows just kind of give us a pictorial of where those would be. All right, so you see what we can do with this. We don't really care about the exact degree, although we do, but what we're going to use those degrees is now we can fix which quadrant of the ball impacted with the object, the rectangular object. So let's see how we're going to use that. All right, so what we can do is we can break our ball or our circle up into quadrants. And so here I've just used some nice 45-degree quadrants. And so I'm saying here that if the degrees is greater than or equal to 315, or in this case less than or equal to 45, then I know I'm in this top quadrant is where I impacted, right? So that was the degrees from the center of the circle to the spot on the rectangle. All right, so notice that's inclusive. Here for the horizontal, so this would tell me I had a vertical impact. If I look here, I can just say greater than 45, because here I said less than or equal to. I don't want to have equal on both, or I'd be confused. Did I have a vertical or a horizontal? So here I'm going to put 45 in the vertical. And then here in the horizontal, I'll just say greater than 45 or less than 135, right? And so if I come down here, I have greater than or equal to 135 and less than or equal to 225. And then here, they're not inclusive. So what I'm saying is I'm favoring vertical because most of the impacts that we'll have in the breakout game are vertical impacts. Between the paddle and the blocks. And then the horizontal will be some blocks where we hit the side of a block or the walls, the side walls. All right. So what we see now that we know, all we need to know is what pair of these did our degrees, our angle in degrees, fall between. Now, if we look at this, this has to be an or. It's either greater than or equal to that, or it's less than that. These are going to be ands. So this will be greater than 45 and less than 135. Same around here, same around here. But because of the zero boundary here, we'll have to use an or here. I'll probably add that to this slide. But once we know, did we have a vertical or a horizontal, now what we can do is use that to modify the velocities of the ball. So if we had a vertical impact, we just take the vertical velocity and invert it by multiplying it by -1. And so in this scenario, our ball is traveling up and to the right. So it's got a positive x velocity and a positive y velocity. We determine the impact was vertical, so all we do is invert the y velocity, but we keep the same x velocity. So now the ball is traveling still to the right, but down. So all we've done is cause it to ricochet downwards. Right, so it's very simple to handle these things. Now, we'll be checking multiple objects, and there could be a chance that our ball is impacted more than one object, and one of the objects provided a vertical, the other a horizontal, and in that case we could end up with inverting both of those. All right, so let's get over and start coding this. I'm going to start by creating a new project. It'll be one of our breakout projects. I'll call this Breakout 08. It's going in my document repositories. And if you updated your template for after Lab 7, whether you were on Windows or if you're doing this in Linux, then your template file should include the new code from the Lab 7. So in my header file, I have the new frame rate variable, and in the implementation file, the CP file, I have my update and render methods and my new timing. And if not, you can just copy the code from 7 and you'll be able to save the new template from Breakout 8. Well, for a while now, we're going to be building on this existing code. So to get things started, we're going to want to develop a function that can determine if we've had a collision between our ball and one of the rectangular objects. And actually, before we get started with that, let's build some rectangular objects. We want to have some border walls. And to illustrate this, without making any code changes right now, I'm going to build my new Breakout 8, which is a good habit anyway, just to make sure everything came over okay. And I'm just going to run it. And notice when our window comes up, we have this very, very thin line representing the window itself, right? And so what we want to do is we want to build some border walls, and we're going to use those border walls to indicate that we've had a collision. So to get started with that, we're not really going to create them as any kind of a game object yet. We'll do that later when we have the ability to create structured objects. For right now, we're just going to recalculate them each time. But we can save ourselves some processing speed if we pre-calculate the wall's coordinates, width, and height. So let's do that. We'll do those as some constants in our header file, and that will greatly speed up our processing. So what we can do is we can do this down here under our game components. I'm going to do it above the, actually I'm going to do it below the ball properties because these will kind of be in the way for a while. So let's do our border walls. Right, and so we need, unfortunately, it's going to be a bunch of properties, and so we'll just need to lay them out, but we can do a bunch of cut and paste. So we're going to start with a constant, and we can just use int for these integers because they're not going to be moving or anything, so we don't need floating point precision in them. But we'll do top wall X. All right, and just for, I'm going to just set them all to 0 here to start with. And I'm going to do a top wall Y, and then a top wall width, and spelling this stuff out will help. Top wall height. All right, so that's good to get us started. Now let's start figuring out what these would be. All right, so, and I'm just going to start kind of in the middle. I really should start at the bottom, which would be the bottom wall and the left wall, because that's where our X and Y are 0, 0. But that's okay. Let's start with the top wall, and we can still figure it out. So if we're picturing here in our Visual Studio this bottom left corner being 0, 0, our top wall starts up here in this top corner on the left and goes over to the right. So our X coordinate is still 0. So our top wall X would be 0, but our top wall's Y needs to be the window height. All right, so the window height, but we want to give some room. We need to come back down however many pixels we want the wall's thickness to be. So let's create that first. Let's do a constant and we'll call it wall size. Or, yeah, that's fine. Wall size. Okay, and then now we can do our wall Y, like we said, needs to be our window height. But then we want to subtract the wall size because we need to come back down and leave room for, we need to come back down a couple pixels so we can fill those pixels in. All right, so the width, well, that's easy. That's the window width, and it's perfectly fine. You'll see we're going to allow our walls to overlap each other in the corners, and that'll be fine. Our height, well, our height will be the wall size. However many pixels, oh, I forgot to set a size. Let's do 2 pixels. So our wall will be window height, which is, you can kind of see it calculated it already. If I scroll over, it's 598 because we go up 600 pixels and then we come back down 2 pixels. All right, so that's our top wall. Okay, so now let's just do our bottom wall next. So what I'm going to do is, if you get used to cut and place, find and replace, you can do things very quickly. So I am going to do a Control H, and I'm going to do top, and notice I selected those lines first. So let me go back through that. Let me cancel that. I want to change top in these 4 lines. So I hold my Shift key and my down arrow and I highlight those 4 lines. And I want to change top to bottom in all of these. So I hit Control H, and notice it says selection here. So those are the lines I selected. And I type top, and I say, well, I want that to be bottom. And then I just do a replace all, and boom, they're all bottom. All right, now I just have to think through. All right, so and I can create a blank line here just to separate. Notice I don't need any comments because they're fully spelled out names. All right, so my bottom wall X, well, that would still start over here at 0. My bottom wall Y, well, that would be 0 also. So let's do 0. My bottom wall's width would be the window width, and its height would be the size. So it'll start at 0 and it'll go up 2 pixels. All right, so that one was easy. All right, so let's copy this again, and let's do the left wall. So once again, I'm going to highlight these 4 lines and hit Control H, and now I'm going to search for bottom, and I'm going to replace it with left. In selection, replace all. All right, so my left wall is going to start down here at 0, 0. So 0x, 0y. Its height, its width, well, let's do that. Its width is just going to be wall size. It's going to be 2 pixels wide. So let's cut this guy and put him here. And then its height, well, that's going to be window height, right? However tall the window is. Like I said, we're going to allow them to overlap in the corners. We'll never see it. All right. One more. Let's do our... So now everywhere where it says left, we want to make that right. Left, right. All right. This is why we create header files, so we can hide all this stuff. Now, the right wall is way over here on the right side, so its X needs to be the window width, but then we got to come back so we leave room for the 2 pixel border. So it's going to be our window width minus our window size, our wall size. All right, it's Y. Well, we can start it down here at the bottom and it'll grow upwards. So it'll still be at 0. So window width minus the 2 pixels for the wall size and 0. Its width will be wall size, our 2 pixels, and then its height will be window height. So let me just double check everything. X window height minus wall size, window width, wall size. Bottom wall X 0, 0. Width is window width, height is wall size. Our left one starts at 0, 0. Its wall width is wall size, so 2 pixels, and its height is window height. Our right wall is going to start at the window width minus wall size. It's going to start at 0 down here at the bottom, and then its width will be wall size and its height will be window height. Okay, so I think that gets our wall sizes. So now let's go ahead and start drawing those. So we're going to come back to Breakout and jump down here to our render method. Let's find our render method. There it is. And let's draw the walls. Now, it doesn't matter in what order we draw these things, because in this we're doing what's called double buffering. I've talked about that briefly, where every time we do a window paint, we swap the buffer that everything was drawn to. So if we were drawing live, then we tend to draw moving objects first and then static objects, because moving objects may dirty up static objects, so we have to refresh them. All right, so it doesn't matter here, but we can kind of keep that same. Let's draw our walls after the ball. Walls. Okay, so to draw the walls, we're obviously using an FGCGL function, and it's one of the draw functions. And if you remember, to draw a rectangle, we just need to use a quad, or a four-sided object. See, draw a four-sided filled block. All right. And then it's going to say that we need the X, Y, width, height, and a color, which we can leave the color to be default white right now. All right, but our X, well, let's say we're going to do the top wall first. So we want top wall X, and then top wall Y, and then top wall width, and then top wall height. All right, and we don't even need to comment this because we've got top wall spelled out all over it. So let's just copy this and paste. And I'm going to paste it for 3 more times, or 2 more times. And then I'm going to highlight that one, and I'm going to do Control H, and I'm going to change top to bottom. In that selection, I'm going to hit Replace All. Okay. And then I'm going to select this one and do Control H, and let's do top, and let's make it left. And replace all. And then I'm going to select this one and do Control H, and I'm going to do top, and I'll make it right. All right, done. Let's see what happens. All right, so remember before we didn't see any kind of border to our OpenGL window. Let's run it now. All right, so now we can see we have a nice thin 2-pixel border displayed around our breakout window. Now if we start moving the ball, notice it'll just disappear off the screen. Let's see if I can get it to come back down. Boop, right through the wall. Okay, so that's what we want to stop now. All right, so to get started, we need to figure out, we want to create a function down here, and I'm just going to start, so we're below main, and since our main logic is process, input, update, and render, we want to keep these methods together in the way we define them, declare and define them down here below. So we have our update and then our render. So our next functions will be below those main functions. So let's do, I've got a nice 1 to 2 spots. I know Python likes 2 spots between functions, so we'll go with that here. Let's start our funky comment. So I create 3 of these so that I can hit an enter. And then this will be our update function. No, I'm sorry, I said that wrong. This is going to be our collision checking function. So we're going to check for collisions between a circle and a rectangle. All right, so what do we need for parameters and what do we need to return? All right, so let's go see if we can figure out what those values are going to be. All right, so looking back here at our PowerPoint presentation, we noticed that to be able to calculate the spot on the rectangle that we need to compare to our circle, we needed to know the circle's X and Y, and then we needed to know the rectangle's X and Y, its height, and its width. So all of these things here we needed to know. All right, and typically we wouldn't use these 2-letter abbreviations, and later we'll spell those out better once we start having using objects to represent these or structures. But for right now, it can get really, really wordy if we try to spell all these out. So we'll just consider these to be some well-known abbreviations, and we will document them in our code. So this represents the items that we're going to need to pass to our collision checking function. All right, and then it should be able to calculate the distance using those and the angle, and then that'll give us the ability to determine the quadrant. What we need back from it is, did we have a vertical collision or a horizontal collision? So those, our returns need to be these values, but notice it's multiple values, vertical and horizontal. We're not sure which value, but we could determine for right now, the way we're doing it, that it's only going to return one of these values at a time. So we can return these in some way to know that it was a vertical or a horizontal from that collision check, because we'll only check the circle with one object at a time, then we'll check the next object. All right, so let's see how that's going to work. All right, so to save time, I've gotten the parameters typed out. So you can pause and go through and type these out for yourself. But this gives us all the parameters that we need to pass to it, our circles, X and Y, the radius of the circle, and then our rectangles, X and Y, width and height. All right, so we can return as an integer value, we can determine if there was a collision in the vertical, horizontal, or none. So let's go ahead and give these some kind of named values. So I'm going to switch over to our header file, and we're going to define some new values. And these will be, we can do these as games, well, not really game settings, not really game components. I'll do them somewhere in the middle. All right, these will be some flag values. And so you can see I've got 3 flag values here. I have collision none, collision vertical, and collision horizontal as integers. And I've made them values 0, 1, and 2. And here I'm just showing what the binary value, and I'm just going to do it as 2 binary bits. So the 0b just indicates a binary. So this is the binary value of 0, this is 1, and this is 2. And what we can see here is the patterns are unique. In other words, 0 is 2 zeros. Vertical of 1 would only have a 1 in the first bit, and horizontal would have a 1 in the second bit, or we call this bit 0 and bit 1, right? And so we can use this to be able to combine both a vertical and a horizontal, which would give us a 0B11. And we would be able to test, is the vertical bit turned on? Is the horizontal bit turned on? All right, so these are now defined as constants we can use as type int. So if we come back over here, we can start to build our function now. All right, so this is going to be our collision check function, and we need all of these values, and we'll pass all of these values here as floats, and we'll return an int. All right, so I've got my return type as int, I've got my function identifier, I'm calling it collision check, and I've got my parameters, my circle X and circle Y, circle radius, my rectangle X, rectangle Y, rectangle width, and rectangle height. I've got the body started. I would want to put an end here, end collision check. And then since my function returns an int, I need to create an int variable here, and I'll just call it quadrant. And I'm going to set it equal to collision none. And then I want to return my quadrant variable. All right, and now we've got the base definition of our function. We know it's a definition because we have the body. So let's go ahead before we forget and get the declaration. So let's copy the definition statement, and then we'll go up to the top where we have our function prototypes. And once again, it's defined under main, so we want to put it under our main function. We need to end it with a semicolon. All right. And it's not updating any of the variables in any of the parameters, so we can pass them by value. We don't need to pass them by reference. And we, of course, have our return type. All right, so let's go back down and start to build the body of this function. Now, the first thing we wanted to come up with was the point on the rectangle that's closest to our circle. And if we take a look back real fast, if we go through just one quick iteration of looking at the circle x, it would have been the rectangle x. If it was greater than the rectangle x plus the width, it was the rectangle x plus the width. Else it was the circle's x. So we could do an if, then an else if, then an else. But what we find is we can actually do away with the else if we just initialize it to circle x. That would be the same way for the y. We'd have the if, an else if, and if we initialize the y, test y, to circle y, then we don't need an else on the statement. All right, so that's what we're going to do. We're going to create two variables here, a test x and a test y. They'll represent the x and y for the spot on the rectangle. So these are the coordinates on the rectangle closest to closest to the circle's center. All right, and so we're initializing them to cx and cy as if the circle's x is between the rectangle's x and the rectangle x plus width and circle y. All right, so next we can find the horizontal coordinate on the rectangle closest to the circle center by first testing, is the circle x less than the rectangle x? And if so, we overwrite our test x with the rectangle's x. Else if our circle x is greater than our rectangle x plus the rectangle width. Oh, we know that the circle is right of the rectangle. And we would make our test x equal to our rectangle x plus rectangle width. All right, now we're just going to duplicate this for the y coordinates. So here you can see in highlighted, we check if the circle y is less than the rectangle y, we set our test y to rectangle y. Else if the circle y is greater than the rectangle y plus height, then we set test y to rectangle y plus rectangle height. And instead of having the else, we've already initialized it to circle y, which would have been the else condition. So now for both Pythagorean's theorem to get the distance and for the arctangent function, we need to get the difference between the circles x and y and the test x and y. So we can create some variables here to represent those. So we'll have a diff x. We'll just set that to test x minus circle x. Like I said, it doesn't really matter which order we do it in. Oh, so I probably need to spell the same, test x, and then a float diff y, and we'll set that equal to test y minus cy. All right, so our next step is going to be to calculate the distance from the center of the circle to the rectangle, the test point on the rectangle, using Pythagorean theorem. And for that, we're going to need the power function and the square root function. So let's go ahead and include the math library. So the math library is a system library, so we need to use Chevron. So we do those before our own library. So let's include math.h, and for we're doing this for square root and power right now. We'll add more to that soon, and then we can come back down to the bottom where we're defining our function, and now we can create a floating point distance. And we don't need super precision, so we don't need to use and we're not going to have really large integrals either, so we don't need a double. We can just use a float, but we want to do a square root of, we want our diff x, we need to raise our diff x to the, we need to square it. So we want to do a power of our diff x to 2, and then we want to add to that the power of our diff y to 2. And notice it really doesn't matter in what order we do these because we're just adding them together. All right, but that should calculate our distance. All right, so now we can test if the circle is closer to the rectangle than its radius, then we had a collision. So we can now do if distance is less than the circle's radius, then we know we had a collision. All right, and I'm going to do end collision so I know where that went, because I think this is going to get a little bit bigger. But if we're in here, we know we had a collision. Otherwise, we should be returning quadrant, which is set to collision none. So it's in here that we'd want to set that to something else. Now looking back at our PowerPoint presentation, we can see we've already calculated our diff x and diff y. Now we need to get our radians, our angle, and then our degrees, and then our degrees 360. So we just need to do these, the arctangent 2, and then our radians times 180 divided by pi, and then subtracting that from 90, and then modding that by 360. Now, we could do all of that in one statement, but if we break it out, then we have the ability in debugging to see what each of these values represent. So let's do that. So we'll start by calculating the radians. So we'll do a float radians, and we're going to set that equal to the a tangent 2, and it tells us we need to pass in the difference y, diff y, and then the diff x. All right, that should give us our radians. And then now we can calculate the angle, but to do the angle we need pi, and we don't have a constant for pi, and I don't want to type out the number and hard code it in here, so we can get a constant, but we have to do something that sometimes may complain. But what we're going to do is we need to modify the math library because there's an old constant that's hidden in it that we can use for pi. Instead of calculating pi, we have to use a special define. All right, so another directive, it's a define, and we have to define use math defines enable mpi. All right, and that allows us to get, we're going to use theatan2 function and mpi defined in the math library. All right, so now we can come back down to the bottom, and in here we can calculate the angle is going to be the radians minus times 180. We want to use a float literal divided by mpi. All right, and notice it recognized it, and we can see it's defined. All right, and this will be relative to the x-axis. All right, so now we want to get degrees, and that's going to be our 90 minus our angle. All right, and then we're going to get degrees 360, or let's just call it cardinal, or our cardinal degrees. And our cardinal degrees is going to be, well, all we need to do is do degrees mod 360. And this will be, so let's do, this will be rotate angle to the left 90 degrees. Why did I spell no, D-G-R-E. Oh, I forgot. The mod doesn't like floating point. It wants it to be an integer. So at this point, we're just going to cut off any decimals, and we'll do the integer degrees mod 360. We can do a floating point mod, but we really don't need to. And then this will be to fix negative cardinal degrees. All right, so those are, and so now we could do a break here and step through these, or we can use cout to print them out. All right, so now I just want to explain a little bit about what we're doing. We're dividing our ball into 45-degree quadrants, with the upper and lower resulting in vertical collisions and the left and right representing horizontal collisions. And since most of our collisions will be vertical, we're going to make the 45-degree radials inclusive in the vertical check. So what do we mean by inclusive? We mean greater than or equal to. So we needed to do, if we look back real fast, we needed to check if the cardinal degrees are greater than or equal to 315, or less than or equal to 45. Or we could say, are they greater than or equal to 225 and greater than, oh, that should have been a less than, and that should have been, no, that should be less than, and that should be greater than, right? Greater than 1 or equal to 135 and less than 225, then it's in this range. So if we only check this range and this range, if it's one of those two, we have a vertical, otherwise we have a horizontal. So we can simplify the checks that we need, but we have to check these values somewhat separately. This is an OR condition. Is it greater than 315, or is it less than or equal to 445? Or is it between those two? so we can do that. We can do it by doing if our cardinal is, and I'm going to do this in another set of grouping. If our cardinal is greater than or equal to 335, sorry, that should have been 315, because 315 and 45 would be 360. If it's greater than or equal to that, or cardinal is less than or equal to 45, then we are in the top quadrant. Right now, I'm missing an ending parenthesis, but I'm not going to put it here. I'm going to put it down here, and then I'm going to say I have this, and I could have done these individually, but I wanted to show them together since they represent the top quadrant. But I'm going to say this or, and then I'm going to do another grouping, and I'm going to say cardinal is greater than or equal to it'll be 135 and cardinal is less than or equal to 225. I'm sorry. Then we're in the bottom quadrant. All right, and if these are true, I don't want to put that there, sorry. I want to put that down here. All right, and this is going to be quadrants. All right, so if this is true, either the cardinal is either greater than or equal to 315 or less than or equal to 45, or it's greater than or equal to, 135 and less than or equal to 225. So if either of those are true, we have a vertical collision. So we would set our return variable quadrant. So we would set quadrant equal to vertical collision vertical. All right. Else, we're obviously in the left or right quadrant. Oops, sorry. I'm gonna put a comment. Oh, why won't it let me? Sorry, it's trying to help me too much. Oh, I see why. I have an extra set of curly braces here. Actually, I have too many here. What happened? There we go. Oh, I see what it's doing. Okay. Let me put the answer here. Quadrant is going to equal collision horizontal. And now maybe it'll let me do it. There we go. I'm just tabbing over so I can say left or right quadrant. All right, so sorry that was painful. So we're saying that if it's in the top quadrant or the bottom quadrant, then we had a vertical collision. Otherwise, we have a horizontal collision. And we know we have a collision because we're inside the distance is less than the radius of the circle. All right? And so then we would be returning that quadrant. All right, so let's go implement this. What we want to do now is in our update method, after we've moved the ball, now we can check to see if we've had any collisions. All right, so here's where we can check to see if our ball has hit one of the walls. So our collision check function is returning an int, so we need an int variable, and we'll call it collision. And we can set it equal to, I'll call it a collision check, and we need the parameters. I'm going to go ahead and put the semicolon here so I don't forget it. And I'm going to come back in here and, well, now it won't give me the help. Let's see if I get rid of that and start it again. Okay, we'll just do it this way. So we need the circles x. Well, that's ball x. And then the circle y is ball y. The circle's radius is ball size. All right. The rectangle's x. Well, let's say we're going to check the top wall first. So we'll do top wall x, top wall y, and then our top wall width and our top wall height. All right, now I can put a semicolon. All right, so, and I don't really need to do any kind of commenting because it's spelling it out that I'm checking the ball against the top wall. All right, so now that would tell me if we had a collision with the top wall. Now I want to know, have we collided with any of the walls? And our collision is coming back, if we look real quick, it's coming back as either collision vertical or collision horizontal, or a 0, 1 or a 1, 0. And I want to know, I just want to know, did I have a collision with any of the walls? So what I want to do is I want to be able to call all 4 of these, and I want to somewhat add them all up, but I can't add. I don't want to add because if I add, I get strange results. I could have a vertical and a horizontal if I happen to hit in the corner, and I might end up with 3, and that's probably the most I could get. But what if I'm hitting 2 blocks in a wall? Now I've got a weird math. But one of the nice things we can do with logic and bits is we can keep combining. So if we were to do a 0, 1 or, and it's just a single, remember it's just a single vertical bar for a bitwise or, we could do that, and the result of that would be the result of ORing each bit. So a 1 or a 1 is a 1, a 0 or a 0 is a 0, and our result would be that. Now, if we did the same thing down here, we ORed a vertical with a horizontal, a 1 with a 0 is a 1, a 0 with a 1 is a 1, and we would end up with a vertical and a horizontal. Now, if I was to get another vertical and OR that to that result, then my new result would be a 1 or a 1 is a 1, a 0 or a 1 is a 1, and that would be, and notice I haven't changed, I haven't lost anything, and I haven't changed anything. It's just allowing me to turn on any of the bits that I need to without modifying, removing anything. So that's what we're going to do. We're going to use the OR operator, and I'm just going to copy this line and paste it. Now I got to get rid of the data type because we already have the variable defined, and I want to do an OR equal. So whatever comes back is going to be ORed to the current value of collision. All right, so all I need to do now is modify where it says top to the others. And before I do that, I'm just going to create 2 more of these for the left and right. And so now I can do my find and replace, Control H, and I want top to be bottom, I'm going to select the next one and Control H, and I want top to be left and replace all. And then I want Control H, and I want top to be right. Okay, and now I've got checking all 4 walls, ORing the collision test back to one collision variable, so I'll know do I have any vertical or any horizontal collisions. Now, since my collision checks are returning one of these values, if I had no collisions, my collision variable should be set to collision none, which is 0. And I can use that in an if statement to say if collision because if it's none, this will be false and we'll skip this if statement. Otherwise, we've had at least a vertical or a horizontal collision. So now I've put in here that for a collision, we invert the velocities and then move the ball half of its radius. Actually, we're not going to do half. We'll just do its whole radius. We'll move the ball its radius in the new direction to get it out of the object it is colliding with, so we don't end up with a second collision on the next update. All right, so remember, things are happening very, very fast in here. And if we leave the ball inside the object it collided with, after we've already moved it into that object, just changing the velocity won't change the fact that it might still be in that object after it moves again and it does the next collision check. So we want to move it. If it was going up, we invert the velocity to make it go down. We want to go ahead and move it down at least its radius to get it back out of the object it collided with. Now first we need to see how are we going to test for a vertical collision. All right, so we are going to do this. First we'll test for if collision and, notice this is just, actually we want 2 ands. If collision and collision vertical. All right. So how is this working? Well, this is the logical and true or false. So true or false, does collision have collision vertical in it? So if we look back again real quick here, if we had a value like this and we test this and that, then a logical and says a 1 and a 0 is a 0. And then a 0 and a 0 is a 0. So we'd end up with the fact that there was that vertical was not turned on in this value, right? By testing with collision vertical, this value here, testing this value. Now, if we did the same thing down here, then we'd find that a 1 and a 1 is a 1. And in this case, a 0 and a 0 is a 0. But we would get back that there was a value. The result is not 0, so it would be true. That collision vertical was in this value. Now, if we did it here, we would get a 1 and a 0 is a 0, and a 0 and a 1 is a 0, and we would get that this value did not contain collision vertical in it, right? And then if for some reason we just happen to have combined a vertical and a horizontal, and we now had a value like this, and we tested this, a 1 and a 1 would give us a 1. And then a 0 and a 1 would be a 0, And in the end, our result would still be considered true that this value includes collision vertical in it. So that's what we're doing here. When we look back in our implementation file, we're saying and collision or collision variable with collision vertical, but don't modify it. We're not doing the single and, which would modify it. We're doing the double and to only do a test and return true or false. So if collision and collision vertical returns a true value, then we know we've had a vertical collision. So the first thing we want to do is we want to invert the velocity. And in this case, the vertical velocity, which is the ball's y velocity. So we want ball velocity y to be, we want to multiply it by -1 to invert it. So if it's negative right now, that'll make it a positive velocity. If it's a positive velocity, that will now be a negative velocity. Okay, next, we want to move the ball in the new direction to get it out of the object. So we're going to move it by its radius to do that. So we will make our ball y, so the ball's y coordinate, we want to add to that. Now we need to know, is the ball velocity positive or negative? So we know, are we adding a positive radius or are we adding a negative radius? So we can use the ternary operator for this, which was an inline if statement, if you'll remember. So let's see what that looks like. So we can test, is ball velocity y greater than 0? We'll do 0.0 since it's a floating point value, right? And now we can test, is that true? If that's true, we'll multiply the radius by 1. Otherwise, we'll multiply it by a -1. Okay, now I'm just going to put all this in a set of parentheses so we can see that that's the ternary operation. In the end, this will result in either 1 or -1. And then we can multiply that by, and I'm going to do this in grouping because I'm going to do the ball size, which is its radius, plus 1. And that way, we don't just move the radius, because the radius now, if we only move the radius, we're probably still touching the object, or we could still be touching the object if we moved in to the center of the circle. We probably didn't, but just in case, if we're going to move away, we'll move the radius plus 1 pixel. All right? And that should get us out of the object. Now we'll see a little bit of a jump if you really focus on it when it hits a wall. But okay, so that does it for, so this is to invert the velocity, and this is the, invert the vertical velocity, and then this move the ball out of object by radius plus 1. All right, so I'm going to copy all of this, and I'm going to do this for the horizontal now. So this will just be collision horizontal. Hopefully that's correct. Okay, so now this just becomes the ball's velocity x, and this is now the horizontal, and then this is the ball's x, and the ball velocity x, and everything else stays the same. All right, so cut and paste is your friend. All right, now later we'll need to test to see if we had a collision with the bottom wall, then that game is over, but we'll add that in later. Right now we just want the ball to bounce around off the walls. Okay, so this should be enough. Let's build. All right, before we run it, I realized I was wrong. We don't want the 2 ampersands in here, which are the logical test to see is this true and is this true. And what we would find is if this has a value and this does have a value, because we know we set it as a constant to a numerical value 1 or 2, then we end up with this being true regardless of whether this is this. So what we wanted to do was we wanted to do the bitwise AND so that the result of this is calculated and is either 0 or 1. And this isn't really modifying our collision variable. It's just modifying the result in this test here, because we're not assigning the result of this back to collision. So we just wanted to change these 2 double ampersands to single ampersands so that we do the result of ANDing these 2 together and then determine if that's got a 0 or non-zero value. All right, so if you build after that, oops, oh, I just did a rebuild, that's fine. And then you run. All right, so we've got our borders. We see our little thin border walls here. And when we run it now, by using the arrow or the WASD to start moving the ball around, if we let it hit a wall, we should get a nice ricochet off the wall. Oh, we have something wrong with the left wall, I'm noticing. All right, so let's see what's going on with the left wall. All right, so it turns out that the C++ modulus operator is not doing what a modulus function would do in some other higher level environment. So we can do it manually. What I've done is I've gone back to making all of my variables floats, and with degrees, one thing I did is I went ahead and added in the 0.0 on the 90 to make it a float literal. But then here in our cardinal, to fix the negatives, I'm using the ternary operator again to check if degrees is greater than 0, then just assign degrees to cardinal. Otherwise, or else, we're going to add degrees to 360. So in other words, we're going to take the negative and subtract it from 260, and that will give us the correct angle that the modulus operator was supposed to do for us. All right, so now if we run this, and we head off towards our left wall, we're going up and left, and now we're going up and right. All right, so if we hit here, we should be doing okay. I'm going to speed it up a little bit. There's our down. Now hit our down wall. Okay, so we seem to be getting a good reaction. Let's see, we even got a multi-bounce off the corner there. Now that probably was 2 different updates. All right. And so the reason you're seeing the ball kind of like lurch forwards and backwards is because we're getting multiple updates at points, because this OpenGL window is not getting dedicated processing and other things are running in the background on my computer, and that's causing the program to slow down in the game loop, and then we get multiple updates. But we can see it's working, so that's good for this lab. I hope you have enjoyed putting this part together. We now have some collision checking in. We are ready to really start breaking some blocks.